light bulbs. In the first case over here where I've got parallel, I have a certain amount of current flowing across each of these. If all these resistors are the same, or in other words, if all the bulbs were the same, then it's the same current flowing across each of them. Adding a new bulb to it does not affect these at all, because the potential drop across each of these stays the same. Because I just take a path, oop. I'm either changing the direction of my current or the battery. So I have current flowing out here, it flows across that one, or it flows across that, or that one. So if I add a new bulb here, what happens is these stay the same. I'm now drawing more current, and so my battery is going to drain faster.
So no matter how many light bulbs you add, it's not eventually going to like dim each of the light bulbs?
Correct, it will not dim the light bulbs.
Okay, it'll just drain the battery faster?
Yes. The other case, when I have in series, if I just have one light bulb in the circuit, it's going to glow, but when I add the second one in there, my current's going to start to drop. Because I have a greater overall resistance, so the amount of current flowing out is going to drop as I add resistors in series. This will not drain as fast, and the bulbs will be dimmer. Now, when a bulb blows, when the incandescent bulb blows, basically, you've heated up the element enough to the point where it snaps. Like I said, it heats, it will expand some, and at some point it will break off so that you don't have that connection anymore. In the series, if one of these breaks, suddenly you've got a gap. And what happens when you have a gap in a circuit?
It starts sparking?
Usually not. That's possible if when the filament breaks, it's right there. If it's close enough, it'll spark. But typically in incandescent bulbs, it breaks off enough so that it's not close enough for a spark.
So you die. Is that what you said?
Not. No.
I said you're in the dark.
Dark.
Oh,
Not
it's
die.
dark. I thought you said you're gonna die, and I was like, okay, that's dark.
It is dark.
If one of these breaks, what happens?
All the others keep going.
Yeah.
Battery lives longer.
Yes. Or your power bill is not quite as high,
Right.
even though we use AC instead of DC. But if any of you have dealt with Christmas lights, they used to have, and I know when I was growing up, so that probably age of your parents, one bulb went out, and all the bulbs went out. Good luck trying to find the one that was dead. And then you've got the parallel ones, which uses more energy, but if one blows, you might not even notice. Or I think what they have now is some combination of it where you've got your power supply here, and then you'll have, a strand like that, and then another strand like this, and so on. So if one of these breaks, yeah, you lose a section of it, but most of it still stays lit.
So the next time I look at Christmas lights, I'm gonna think about physics.
Excellent. Questions before we make this more complicated? All right, let's make it more complicated.
Can I ask a quick language question?
Yeah.
Is there a difference between resistance and resistivity?
Yes. Resistivity, resistance is ultimately what affects current, and I can create resistance several different ways because in the basic formula, I've got 3 variables there. one of which is resistivity.
Mhm.
But if I have, let's say I need a wire this long, I'm gonna get different resistance depending upon what the material is, which affects the resistivity.
Okay. They're both a capital R though, right?
No, resistivity is the rho.
Oh, that's right. Okay. Okay. Thank you.
Yeah, resistivity is definitely a material-specific number that you can look up. Resistance has a lot of things involved.
So if you gave us a problem, you would just provide rho based on the material?
Yes, or
Or we solve
there
it?
have been questions where I've said, what is the resistivity?
Right,
Which I've given you the other information.
I see, okay. Thank you.
Let's see, let's get some numbers here. So 1 ohm, 2 ohms, 3 ohms, 4 ohms, 5 ohms. Volts. What is the current flowing across each resistor? That's where we're heading right now. So current across each resistor.
So you're not looking for the equivalent resistance, you're looking for the current across each of those 5
Yes.
resistors. So like I1, I2, essentially.
That's probably the way I'm gonna label it. Brooke?
So all you have to do is the 10 volts divided by each one of the resistors?
No. It's more complicated than that.
Okay, I was gonna say, that's not the complicated thing I was expecting.
All right. The way you handle a problem like this is you take it down piece by piece. Now, there are many ways of solving it. The fact that there's only one power supply and the rest of it are resistors in series or parallel, I'm gonna take one tack for that. There's another method of solving this that we will do later for more complicated problems, but for something like this, some students actually prefer the more complicated way because they learn how to do it and they'll apply it to all the situations. I am not gonna present the more complicated way at the moment. So the first thing I actually am gonna do is, I do notice that the current coming out of my power supply is the current that has to flow across my 1 ohm resistor. So I1 would be the current coming out of the power supply. So I actually am gonna find the equivalent resistance first. So even though I haven't asked for it specifically, it's just part of the technique that I'm doing right now. So my equivalent resistance, well, first off, I've got these in parallel. So that would be $20. So that stays 1. I got my 2 right there, I got my 3 right there, and then this would be what I'll call R45, which I think is 29ths. It is? Okay. I now have these in series, and I just add them straight up. So I've got my 1, splits into a 2, and then going to the top path.
47 lights on the top.
I now have these in parallel, because I have a junction at both ends, and so 9/47 plus 1/2. And I assume someone's about to tell me.
Well, taking the reciprocal, I ended up with 5.72 ohms.
That does not seem right.
It may not be. I took 47 ninths and, oh, I gotta flip that. Point 0.69? Does that seem better?
When I'm adding things in with the addition of the reciprocals, the final answer should be smaller than whichever is the smaller value.
Right.
So if I'm doing capacitors in series, then like total should be less than whatever the smallest capacitor is. Adding resistors in parallel, it should be less than the smaller one.
That makes sense, okay.
So 0.69
Ohms.
ohms. And so my total resistance, or my equivalent resistance, probably better wording, 1.69 ohms. And that was a 10-volt battery. And so the current coming out of the power supply will be 10 volts divided by 1.69 ohms, which is somewhere around 6. It's 6 exactly?
No, it's 5.9.
Okay. There is a lab that sometimes do, which has 7 resistors in it, and you basically go through this and do the calculations. If you don't take it out to at least 4 decimal places, your results are going to get screwed up. And so, probably getting into the habit of taking a couple extra decimal places is a good thing. For what we're doing right here, we can deal with it, but there is a lab where you really do need to take it out more.
So the 0.69, that's the 0.69 ohms, is that from taking the reciprocal of 9/47 plus 1/2?
Yes, you add those together, then take the reciprocal. You got something different?
Yes.
Yeah.
What'd you get?
1.446.
1.446?
Yes.
My bad.
I got 0.69 at first, but it's because I didn't divide it,
Yeah.
or I didn't take the reciprocal.
Oh, okay. So that means this would be 2.446.
Was 1.45 the new number? 1.446, okay.
Yep. And so this puts it 4 point something. 4.1.
How'd you get the 2?
Because now I have a 2 ohm resistor and a 1.446 ohm
Oh, so
resistor.
you just added it.
Yeah. The first thing we did is that, we get this, and then we added these, that, then we added these, that, and then we added these
Okay.
together. Is it 4.1?
Yeah.
Okay. So that's the current flowing out of the battery. That has to be I1, that has to be the current flowing across the 1 ohm resistor right here. So I now have at least that piece of information, so I1, and I draw the arrow in the direction that the current's flowing, is equal to 4.1 amperes. So now let's figure out what is the potential drop across the 1 ohm resistor. Well, I've got a 1 ohm resistor and I got 4.1 amperes flowing across it. What is my potential drop? Hint, use Ohm's law.
What is the current that flows?
No, what's the voltage across this resistor here? What is, don't tell me?
No. That wasn't,
What is Ohm's law?
I don't know.
I is equal to change in voltage over R.
Okay, or delta V is equal to IR. What's the resistance?
1. Oh, so it's equal to the current.
With different units. Yeah, it's just multiply that times that. So when I'm going in the direction of current flow here, my voltage is negative 4.1 volts. All right, so I have 10 volt battery here, so let's do our Kirchhoff loop rule here. I start at this point, I have 0 volts. I gain 10, I lose 4.1, I'm losing something else, and I get back to where I started. So how much am I losing going across the 2 ohm resistor?
5.9.
Yep. So when I'm going in this direction, I lose 5.9 volts. So therefore, what is the current across the 2 ohm resistor? Again, use Ohm's law.
It's either multiplied or divided by 2, depending on how you manipulate this, but.
Well, we got negative 5.9, or 5.9, is equal to I times 2.
Right, so divide by 2.
How did we get the 5.9?
Again, Kirchhoff's rule is I start at some point, I end up at 0 total. So I gain 10, I lose 4.1, that's what we figured out just then. What else? And then I lose something else, and I get back to 0.
Okay.
So I lost 5.9, because 5.9 and 4.1, it adds up to 10.
Is that between both the three? Is the 5.9 that we are?
That's just for this.
That's just for that?
Yeah.
It's not for the 3 ohm resistor or?
Nope. Well, that 5.9 applies to
To
all of that up there, not any of them individually.
Right, because we added them together over here, or?
Right, or, let's give myself some more space there. That was the 3 ohm, and it splits 4 ohm, 5 ohm. To get this 5.9 here, all I did was take this path right here. So I have not taken that path up there. I don't know what the individual loss on any of these are yet, but I know that I gain 10 here, I lose 4.1 going across that, I'm gonna lose something here, lose something there to get back to 0.
And that's what we're finding out?
Yes.
Thank you.
So my current flowing across here, trying to maintain some color coding here, is that my current flowing down this path would just be 5.9 divided by 2, which is 2.95 amperes. If I did the math right.
Yes, you did.
2.95.
So now let's think about the junction. I got a junction right here. I have 4.1 going into it. I have 2.95 going off to the right. How much is going up? What would that current have to be?
Difference between those two.
Yep. Which is 1.15 amperes. Going this way. And that has to be the current flowing across the 3 ohm resistor. There's no junction. Once that 1.15 amps goes this way, it has to go through that. So what is the voltage across that resistor?
1.15 times 3.
Yep. So 3.45 volts. Well, we lost.
Is the 2.95 amps, is that,
Yes.
that's positive?
Yes, because I know the current's flowing this way, and so the positive current means it's in the direction that the arrow is pointing.
Okay,
If you like, you can point the arrow in the other direction and call it negative.
okay.
I don't know if there's a better way to write this, but I've been writing subscripts, like writing like delta V sub 2 or delta V sub 3 to indicate the like change in potential at each of those resistors. Is that
Yeah,
how
that,
we're supposed
okay,
to write
so
that?
this would be delta V1,
Okay,
this is delta V2, delta V3,
okay.
this is I3.
So delta V3 would be 3.45 volts?
Yes,
Okay.
so now we can figure out what the potential drop across the 4 or 5 is. I start here, I gain 10, I lose 4.1, I lose 3.45, I take this path up here, I lose whatever's left over to get back to 0. And doing the fancy math here, that would be, I lose 2.45. Either path I take.
No, they'd be the same, even though the resistance is different. They have
Because
the
they're in
same
parallel,
voltage.
first off. Parallel, the voltage is the same,
Right.
because it doesn't matter which path. The current will be different, that's what's
Right.
gonna differ between the two. So 4.1, 4.1, 3.45, 2.45, 0 carry the 1, 0 carry the 1, yep, okay. Okay. So now I can find the current flowing across here by dividing by 4. 6.125 amperes going that way. That is not right.
Is it,
0.625 or 6025.
it's 3.45 divided by 4, right?
No, 2.45
Oh, sorry.
divided by 4.
6125
0.625?
or 6.6125.
125, okay. So I have 1.15 amps flowing into the junction. I know 0.6125 goes up this way, so the difference would be what goes across here. Or I do 2.45 volts divided by 5, and I should get the same answer. Or at least close.
2.45 divided by 5
Yes,
is 0.49.
say it again.
0.49.